Welcome back. So in the last lecture, we derived the forward Euler and backward Euler numerical integration schemes, essentially using the finite difference derivative approximation of dx dt. And we derived it for a generic nonlinear ODE, but we also looked at what would happen if our dynamics were linear, if x dot equals ax. What would these two different schemes be? We found that, for example, forward Euler is just the first two terms in the Taylor series of e to the a delta t. Now what we're going to do is we're going to code this up on a really simple example of the spring mass damper system. So I'm going to re-derive, I've already done this before, but just really quickly, just as a refresher, I'm going to derive the equations of motion. We're going to find the A matrix. This is a linear system, so we're going to be in this case here where we're simulating these linear versions of forward Euler and backward Euler. And we're just going to play around with this a little bit in Python and Matlab and see what happens, for example, if I make delta t really big or really small, what happens to these schemes. And I'm actually going to compare this to something called the Runge-Kutta, the fourth order Runge-Kutta scheme, which is a much, much higher accuracy, higher order scheme. If you like, it basically approximates more terms in the Taylor series. It's a better approximation and has better error properties. And so we're going to compare the solution of this with these numerical schemes with that higher order accurate Runge-Kutta scheme. And then in the next few lectures, I'm going to talk about deriving from Taylor series, what is the error of this approximation? And similarly, what are the stability properties of these systems for different delta t's? Okay, good. So I'm just going to really, really quickly rederive from scratch the kind of equations of motion here. So we have some mass m. Remember that our position is measured from some rest position. So x, the position here, is measured with respect to some rest position. And we have Newton's second law. Mx double dot equals minus k times x. That's our spring constant k, so that's the restorative spring force, minus some other constant x dot. That's the damping coefficient c. And if you like, we can move all of these over to one side and divide by m, and we get x double dot plus c over m x dot plus k over m x equals 0. This is kind of the normal form that we're used to writing higher order differential equations in, because from this you could read off the characteristic equation and compute the eigenvalues and e to the lambda t's and solve the system. And so what we're going to do is we're going to introduce these variables omega naught equals the root of k over m. And we're also going to introduce this zeta equals our damping coefficient divided by 2 root km. And if I introduce those two variables, we can essentially write our differential equation x double dot plus 2 zeta omega naught x dot plus omega naught squared x equals 0. Now this looks like maybe I just made things a lot more complicated by introducing these, but these zeta and omega parameters are a much more natural parameter system to understand the dynamics of this spring mass damper. So specifically, omega is the natural frequency, and that only depends on the spring constant and the mass. And this damping coefficient here, this damping ratio, this zeta tells me if my system is overdamped or underdamped or critically damped. So those are things you probably remember from your kind of differential equations or physics class, is that I have these different cases. So case 1 would be if zeta is less than 1, this is underdamped. And that means that the system oscillates. So system oscillates with this frequency. So system oscillates. If zeta is greater than 1, and sorry I wrote such a bad zeta, if it's greater than 1, then it's called overdamped. And overdamped means that basically it does not oscillate. So you let this mass go and it immediately goes back to rest without overshooting and oscillating and dying out. So overdamped means it actually has no oscillations. And if you like, it means that the eigenvalues here have no imaginary part. The roots of the characteristic equation, the roots of the quadratic, the quadratic formula, if I wrote this down in characteristic form, lambda squared plus 2 zeta omega naught lambda plus omega naught squared equals 0, and I solved for lambda. For zeta that are greater than 1, this polynomial in lambda, the roots have no complex conjugate imaginary parts, and so there's no oscillation, there's no sine and cosine to that behavior. This all, of course, relies on what I taught you in the earlier ordinary differential equations lectures, so if you don't know what I'm talking about, you need to rewind to the characteristic equation in the spring mass damper lecture. So that's what overdamped means, and if I have zeta equals 1, that's called critically damped. Critically damped. And so essentially what this means is that in this form, zeta and omega give me some kind of knobs to play with to change the behavior really easily of my system. Instead of changing m and k and c and kind of just randomly guessing what will make it oscillate and what won't, by making zeta greater than 1 or less than 1, I can make it oscillate or not oscillate. Pretty simple. Okay, and so this is the system we're going to simulate with forward Euler and backward Euler, and in particular, I'm going to turn this into a matrix system of first order equations. We've done this a lot of times, and so the way we're going to do that is we're going to introduce this variable x dot equals, maybe I'll just do it over here. So I'm going to introduce my, my variable x dot equals v, and v dot equals all of this stuff on the right. So that would be minus 2 zeta omega naught v minus omega naught squared x. And I can write that as a system of differential equations ddt of x and v. That's my state of my system, my x here. ddt of x and v is going to equal 0, 1, and minus omega naught squared, and minus 2 zeta omega naught times x and v. So this is a matrix system of first order differential equations. And if you like, this looks exactly like x dot equals ax for some vector x. So this is, this is my vector x dot. This is my matrix A, and this is my vector x. So this is the system we're going to be simulating in Python and in Matlab. And specifically what we're going to do is we're going to step the system forward in discrete delta t's using our forward Euler and backward Euler integration schemes, specifically using this integration scheme and this integration scheme since our dynamics are linear. Okay, I'm going to erase this, fire up Python and Matlab, and we're going to code this up and play around with things like zeta and omega and delta t and look at the behavior of these systems. All right, stay put. Okay, so we are simulating this spring mass damper system. So our spring mass damper, I erased the little diagram there, so it's just my mass on a spring with some damper. And we're going to do this in MATLAB and then in Python. And so I've actually already coded this up. I'm going to put a link to the code in the description, both in MATLAB and Python, so you can follow along. But basically what we've done is we've picked some omega natural frequency and some damping ratio. So zeta here is a d. Zeta and d are the same thing. I just didn't want to write zeta a bunch of times. And so this is my system. My A matrix is 0, 1, minus omega squared minus 2 times zeta times omega. This is the right-hand side of x dot equals ax. And what we're going to do is we're going to simulate this using forward Euler, using backward Euler, and also using a much more accurate scheme called a fourth order Runge-Kutta. And we're going to compare those. And we're going to play around with things like delta t. Maybe we'll change the natural frequency and the damping ratio, and we'll see how those systems behave. So I'm going to start with this system with a small delta t, because remember, this is essentially using a finite difference approximation of my derivative, and that is only accurate when I use a small delta t. So let's use a really small 0.01 delta t here. And we're going to integrate from time 0 to time big T equals 10 with this initial condition. So this corresponds to an initial position of 2 units with a 0 velocity. That's what I mean by 2, 0 is position 0 velocity, position 2 velocity 0. And then I'm going to walk you through this forward Euler step and my backward Euler step. So for forward Euler is pretty easy. I basically am going to create this state x big F. That's my forward Euler state. And this is going to be a matrix where each column is x and v at that time step. Okay, so it's going to be advancing forward in time. And so the first column is just x naught. It's literally just x naught, v naught. And then what I'm going to do is for each time, I'm going to take my kth column. Here I am. I'm going to take my kth column, and I'm going to multiply it by this matrix, the identity plus delta t times a times my kth column, and that's going to be my k plus 1th column. That's going to be x k plus 1. And I'm storing all of these in a matrix so I can plot them later. You don't technically have to store this in a big matrix. This is actually really inefficient because I didn't even declare the size of this matrix. So every time step, it's actually creating a whole new matrix and making it bigger and bigger and bigger. This is like terrible MATLAB code. Bear with me. You could have pre-allocated this as a big array, or you didn't have to save this as a matrix if you don't care about plotting, if you just want to know the future trajectory. But I want the whole trajectory x at every intermediate k, so I'm saving them in this big matrix xf. And again, you can convince yourself that this formula here is exactly this formula here. Okay, starting with the 0, the first column is my initial condition. And then I'm going to plot the first position, which is x. If I did xf2 comma colon, that would be plotting the velocity, but I'm just plotting the position, the first entry of this, the first row of my matrix. Okay, so that's forward Euler. Then backward Euler is very, very similar. Except now the update, all of these are going to be stored in XB. So XB is again a matrix where every column is the state of my system at a different instant in time. So the first column of X backward Euler is just X naught. And then my K plus 1th column, my K plus 1th state, is going to equal the inverse of my identity minus a delta t times my kth column. Pretty simple to code this up in MATLAB because the inverse is easy for a matrix. It would be much harder for a generic nonlinear system, x dot equals f of x, but it's easier for a linear system to solve for this implicit Euler. Okay, so that's that. Similarly, I'm going to plot the x position. And then I'm going to show you, I'm just going to, I'm going to plot these things, and I'm going to have a third plot, which is a much more accurate scheme called fourth order Runge-Kutta. And in a few lectures, I'm going to derive the fourth order Runge-Kutta. I'm going to write it down how to actually code this up and solve it, and we're going to look at its error properties. For now, we're going to take it for granted that it's just a really good high order integrator to compare against. Okay, and so the way you do this is it's actually built into MATLAB. This ODE 45 is a adaptive step fourth order Runge-Kutta scheme. So the adaptive time step allows you to bump the accuracy up to fifth order, actually, but it's based on a fourth order Runge-Kutta time stepper. And what this ODE 45 function expects as arguments, it has 3 arguments. It expects the right-hand side of a differential equation, ODE function, the right-hand side, either a times x or f of x. It expects a time span that we're integrating, 0 to big T in increments of delta t, and it expects an initial condition x naught. Okay, and what do I have here? So I'm defining my ODE function. Like I could have defined a function, like a new function, my right-hand side or my linear function or my spring mass damper function, whatever, as a times x. But you can do this on the fly inline in MATLAB using this thing called a function handle. So what this does is it defines a function of time and space, and I'm defining that function to be a times x. Because MATLAB is expecting this ODE fun to possibly vary in time and space. Even though this doesn't change in time, I'm telling MATLAB that it's a function of t comma x. Okay, and so this is how you integrate that right-hand side really, really accurately with fourth order Runge-Kutta. So I'm going to plot all three of these and compare them, and then we're going to play around with the system parameters and see what happens. Okay, good. And then I have some plotting commands to make sure that it doesn't look terrible. Okay, good. So this is the plot. This is what the system dynamics. So I must have picked a damper D that was underdamped. So D is less than 1, so this is underdamped, which means it oscillates, the mass oscillates as it dies out. And that's exactly the behavior you see here, is that it started at position 2 and it's oscillating as it dies out to 0. This is the position versus time. And you can see that all three of these agree pretty accurately, or pretty closely. So for all intents and purposes in this example, the fourth order Runge-Kutta scheme is kind of the truth because it's very accurate. And so that blue curve is kind of the truth here. And forward Euler and backward Euler are the white and the yellow curves here. And so you can actually see, maybe I'll zoom in a teeny tiny bit here if I can. Yeah, let's see if I can zoom in right here. You'll actually see that forward Euler and backward Euler, kind of forward Euler overshoots and backward Euler undershoots compared to this very accurate ODE 45. And remember, just like the finite difference derivatives, the forward difference and the backward difference would kind of overpredict or underpredict. Or when we did our left rectangle rule and right rectangle rule integrals, some of them would overpredict and underpredict based on the slope. It's kind of the exact same thing here because these are different Taylor series approximations to this derivative x dot. But they're not too bad, they're not too inaccurate. Let's see what happens when I change delta t. Okay, so what I would expect is that if I make delta t even smaller, all of my integrators should get closer to each other. They should get more accurate because I haven't derived the error properties yet, but we're pretty sure that these are going to, the error will decrease when I make delta t smaller here. So I just made delta t 10 times smaller. Let's see what happens. Now all three of these curves are perfectly on top of each other. They're almost identical. If I zoom in, you can see that they are different. Let's try this. I'll zoom in a little and you'll see I think that they actually technically are a teeny tiny bit different, but they're much, much closer than before. So making delta t smaller did make all of these integrators better. And I would imagine that making delta t bigger, so that I just made it 10 times smaller, now I'm making it 10 times bigger than my original case. This should make it all much worse. Ooh, that's bad. So forward Euler went unstable. For a delta t of 0.1, this forward Euler scheme actually went unstable. It's saying that the dynamics are blowing up to infinity as time goes to infinity, which we know is not true. We know that the actual system is damped, and these have, negative real part of their eigenvalues. It's a stable system. You can check that. In fact, let's check it right now. Let's look at, eig of a. This has negative real part. It is a stable system. But somehow, for a big enough delta t, this scheme blew up. And it's probably going to have to do with the eigenvalues of this identity plus delta ta. In fact, I bet that thing has unstable eigenvalues, and we're going to show that in the next lecture, that for some delta t, this thing goes unstable. I'm pretty sure that backward Euler remains stable here. So what am I going to do? I'm going to comment out my forward Euler so it doesn't mess everything up. Going to get rid of my legend. And in fact, my backward Euler is still stable, even for a very large delta t of 0.1. Now, it's not very accurate. It doesn't really have the right behavior. It's inaccurate, but it's at least not stable. It's at least not blowing up to infinity. Okay? So this kind of shows a few things. It shows that, I'll go back to my original delta t equals 0.01. So for a moderate delta t, both integrators perform okay. They're not perfect, and making delta t smaller makes them more accurate. But for a big enough delta t, this forward Euler went unstable. So that's a huge limitation of this method, is that it is very prone to instability for even moderately large delta t's. Okay, and I'll tell you why in the next lecture, why this thing is unstable for large delta t's. It's pretty interesting, and it's related to the eigenvalues of this matrix here. Whereas my implicit Euler was still stable even for that larger delta t. It was very inaccurate, but it was more stable. Eventually, for a big enough delta t, even this one will go unstable, but it's much, much, much more stable in general than this scheme here. OK, I think that's pretty much everything I wanted to show you in MATLAB. So now I'm going to switch to Python, and we're going to kind of go over the same stuff. All right. OK, good. So we have derived these equations of motion, x dot equals ax for the spring mass damper system. It is a linear system, so it's x dot equals ax with this A matrix. This A matrix has eigenvalues with negative real part, which means the system is stable. So for any real damping, the system is going to be stable. You can check that. And now what we're going to do is we're going to simulate we're going to predict a trajectory of the system. We're going to simulate the system forward in time using forward Euler and backward Euler in Python. And we're also going to compare this against a third integration scheme, which is called a fourth order Runge-Kutta scheme. I am going to derive it in a future lecture, and we're going to analyze it a bunch. But for now, we're just going to take for granted that fourth order Runge-Kutta is a very, very accurate integrator, much more accurate than these. And that's going to serve as our kind of ground truth for this example. So we're going to compare these against a much more accurate integrator and see how these perform. OK, so I'll just walk you through this. It's pretty simple. I should probably run these good. OK, good. So we've defined our omega and our damping ratio. And so here I've renamed zeta as d, because I didn't want to type zeta a bunch of times, but d and zeta are the same thing. D equals 0.25, zeta equals 0.25 is underdamped. So it's less than 1. So it means we're going to get oscillations in this system. That's good. And we're defining our linear spring mass damper system, our A matrix, as an array, 0, 1, minus omega squared, and minus 2 zeta times omega. And we're going to start by integrating with a small delta t, 0.01. Because again, both of these schemes are based on a finite difference derivative of x dot. And we know that finite difference derivatives are only accurate for small delta t's. So we're going to start with a small delta t. We're going to integrate from time 0 to time big T, so 10 full time units in increments of 0.01. And we're going to start with an initial condition of 2, 0, which corresponds to a position of 2 and a velocity of 0. So 2, 0 means a position of 2, and I let this go with 0 velocity. And then we're going to integrate through forward Euler, we're going to integrate through backward Euler, and I'm going to compare against that more accurate fourth order ODE solver I talked about. So forward Euler is really simple. It literally just, this is some stuff you need to kind of, some preamble, but the real code is down here. So what we're doing is we're storing our forward Euler trajectory in this array xf, x times x big F. And so this is a matrix with each column is a state x and v, x and v, x and v, x and v at each time instance. So the first column of xf is my initial condition. The second column is going to be x1. The third column is going to be x2. The fourth column is x3, and so on and so forth. And again, remember that we start our indexing at 0 in Python. So this big xf array is going to store my trajectory as it evolves in time. So the whole first row is going to be a trajectory of my position. The whole second row is a trajectory of my velocity. And this line here is this forward Euler update. So it says that the k+1th entry, the k+1th step in my trajectory is going to be my kth term times an identity plus dt times a. Okay, a 2 by 2 identity plus a delta t times my kth x equals my k+1th x. So this is the update, and we basically write a for loop, so we keep constantly stepping this thing forward and updating it and building this trajectory xf. Backward Euler is exactly the same thing. Where now what we're doing is we're storing it in this XB array, the exact same trajectory information. Every column is my state at an instant in time. We initialize it, so the first column is my initial condition x0. And now the update, I'll scroll over a little so you can see. This is unfortunate. Let me make this a teeny bit bigger. The update, the k+1th entry of this backward Euler scheme is the kth state xk times I minus a delta t inverse. This is np.linalg.p inverse. That's the inverse of identity minus a delta t times xk. So again, all that we're doing here is we're just coding up this, this backward Euler integration scheme. Again, these are only, the ones I've actually written down here are only for linear x dot equals ax, but it's much easier to solve this implicit backward Euler for linear dynamics because it's just a matrix inversion. Okay, so now we have forward Euler, we have backward Euler, and then we're going to plot those trajectories, and we're going to plot them against this fourth order Runge-Kutta. Fourth order Runge-Kutta is pretty easy in Python. There is this solve IVP, solve initial value problem, where it takes in an ODE function. That literally means the right-hand side of a dx dt equals ODE function. And here we've defined our ODE function to be a times x, because we know that x dot equals a times x. And we're integrating from time 0 to t with initial condition x naught. Pretty simple. So I'm going to run this. And now we're going to plot all of our data here. So this is our x position. We're just plotting, you know, let me scroll up. We're plotting our forward Euler, our backward Euler, and our fourth order Runge-Kutta. And we're plotting the first row, which corresponds to our position. Kind of the 0 index here means our first row. That's the x position in time. So this is literally a plot of x in time. And as you expect, if I pull this thing to a unit 2 and let it go, it's going to oscillate and die out. That's what we see here. It oscillates and dies out. And in particular, you actually see that forward Euler and backward Euler are pretty close to the much more accurate fourth order Runge-Kutta, this ODE 45. And forward Euler overshoots a little bit, and backward Euler undershoots a little bit. So this one's a little bit more unstable, and this one's a little bit more damped or more stable. And you can see that here. You can also plot the velocities if you like, kind of the same story, not much new information by plotting the velocities, but you can plot that. So what do we want to do now? Now I think what would be interesting is to do things like, let's change the delta t. Okay, so we know that because these are based on finite difference derivatives, if I make my delta t smaller, it should make both of these integrals more accurate. So if I do that, I'm going to run this for a smaller delta t. And now when I plot, these curves should get closer together because they're all going to be more accurate. And in fact, yes, they all now collapse on top of each other because I made my delta t 10 times smaller, which means that I've made everything much more accurate. I haven't told you how much more accurate yet. I'm going to derive the accuracy of these schemes in the next lecture. But we know because they're based on Taylor series that making delta t smaller should make them more accurate up to some power of delta t. And that's exactly what we see here. Now let's try making delta t, instead of making it smaller, let's make it 10 times bigger. So go from 0.01 to 0.1. Same thing, now I'm going to plot. Oh no, something went really wrong here with forward Euler. So forward Euler actually went unstable. And it's not like the system went unstable. The spring mass damper system is still stable. The omega and zeta didn't change. All I changed was delta t of my integrator. So the system should still be a damped oscillation, but forward Euler is blowing up to infinity. So again, this is something I'm going to tell you a lot in the next lecture, is how to analyze the stability of these integrators for different delta t. And long story short, I think we all know that it's going to have something to do with the eigenvalues of this operator identity plus delta ta and inverse of identity minus delta ta. These are going to have eigenvalues, and those eigenvalues are going to tell me if my system blows up for some delta t. And what we found here is that for big delta t, forward Euler is unstable and blows up. If I omit this plot, if I just, let's say I just omit my forward Euler. Okay, I'm just going to only plot backward Euler and Runge-Kutta. Actually, backward Euler is still stable. The yellow curve here, even for a big delta t, it still converges to 0. It's very inaccurate. It doesn't match the true behavior of the system hardly at all, but at least it doesn't blow up to infinity. So for a big delta t, forward Euler went unstable, and backward Euler was still stable, even though it's very inaccurate. So we'll understand both of those when we start looking at the eigenvalues of this. That's kind of a generic property of forward and backward Euler, is that forward Euler tends to be very finicky and unstable for even moderate delta t's, whereas backward Euler is typically much more stable. Still not that accurate, but much more stable. Okay, and I'll just go back to my original delta t equals 0.01, and we'll plot it one more time just to leave all of these up. Okay, let's run that one more time. And again, this was for a moderate but small delta t of 0.01. It behaves kind of like you'd expect. Okay, good. That's what I wanted to show you today, is how to code these up and how to play around with the delta t's and see what happens. I think what I'm going to do then in the next lecture, as I've alluded to several times, in the next lecture what I'm going to do is we are now going to look at the error properties. The error properties. What is the error is it order delta t? Is it order delta t squared? We're going to get these from the Taylor series, of f of x of t plus delta t and things like that. And we're also going to look at the stability as a function of delta t. So when I make delta t bigger or smaller, how did the stability of these two numerical schemes change? Okay, that's all coming up. Thank you.